Welcome everyone. In this video I will talk about moment generating function, and in particular I am going to consider a four distribution: binomial, Poisson, negative binomial and geometric distribution. So I'll be discussing the moment generating function of each of them, and in the process I will also be talking about how to calculate their mean and variance. So since we are going to talk about moment generating function concepts and all the four probability distribution, it will be a long video and you need to watch it till the very end to get the concept better. In the beginning you may feel like it is slightly confusing, but if you listen carefully you will understand. So the moment generating function of a random variable x about the origin having the probability density function or probability function f of x is given by. So moment generating function of the random variable x is expectation of e to the power tx. And how do you calculate the expectation of e to the power tx? In case of continuous random variable, it is integration of e to the power tx f of x dx over the entire range of x. And in case of discrete probability distribution, it is e to the power tx into f of x, and summation is taken over the entire range of x. The t here is a real parameter, and it is assumed that this integration and this summation is absolutely convergent, right? Don't get confused with this difficult sounding word, right? So we just basically mean that they are absolutely convergent. Now to understand it better, what I am going to do, I am going to explain certain things here, so just understand it. So what is the definition of moment generating function? We are calculating the expectation of e to the power tx. And if you look at the name itself, it is telling you that we are going to calculate the moments. That is why it is defined as moment generating function. Something which generates the moment is known as moment generating function. I think you must have seen it earlier also, that if I talk about moments of any random variable x about origin, it is represented as mu r dash, and mu r dash is nothing but the expectation of x to the power r, right? And if I ask you what is expectation of x to the power r, in case of continuous random variable, it will be minus infinity to infinity x to the power r into f of x dx. And if I ask you what is the moment of rth order moment for discrete random variable, so it will be summation of x to the power r into f of x, and the summation is taken over entire range of x. So this is what is rth order moment. Again I repeat, what is rth order moment of a random variable x? It is expectation of x to the power r, and which is represented as mu r dash, and I am calculating the rth order moment about origin. So now I will not be speaking this term again and again. When I am talking about mu r dash, basically the rth order moment about origin. And what is the rth order moment? It is expectation of x to the power r, and how it is calculated? It is calculated by using these two formula. But the moment generating function can help us to calculate the rth order moment or any order moment with the help of this function. So how it can be calculated, that is what I am trying to explain. Before I write the expansion further, I just want to I want you to remember that you all have studied about the exponential expansion e to the power x, and it is 1 by 1 plus x by factorial 1 plus x square by factorial 2 plus x cube by factorial 3, and so on up to infinity. So if I continue it from here, I mean this was just to recall certain things. So if I continue from here, expectation of e to the power tx, so it will look like 1 plus tx by factorial 1 plus t square x square by factorial 2 plus t cube x cube by factorial 3, and so on up to infinity. And basically I have to calculate the expectation. So actually this is what I need to write. Now there is a property of expectation. I hope you know that, but if you don't know, I'm just look at this. So expectation of this thing can be written as 1, and just let me write that we have seen this property that expectation of a plus bx is equal to a plus b times expectation of x. This we have seen earlier. It can be generalized, so it can be written as 1 plus t by t is a real parameter, so it will be t by factorial 1 expectation of x. Then it will be t square by factorial 2 expectation of x square. And in general, if I can write here the general term also, so that you are clear about. So let me write a general term, t to the power r x to the power r here by factorial r up to infinity. So in general, this will be like what? Plus t to the power r by factorial r expectation of x to the power r. In terms of mu r dash, what is expectation of 1? Expectation of 1 is mu 1 dash. So I can write it t by factorial 1 mu 1 dash, t square by factorial 2 mu 2 dash, and so on. And the general term can be written as t to the power r by factorial r mu r dash, right? So did you realize one thing, that if I am writing the expansion of e to the power tx and taking its expectation, we are getting the moments of different order. This is the first order moment, means this is the expectation of x. This is the second order moment, means expectation of x square. This is the rth order moment, that is expectation of x to the power r. So if I have to calculate the rth order moment, means if I have to calculate mu r dash, it is what? It is the coefficient of x to the power r. Just look at this. It is the coefficient of, sorry, not x to the power, t to the power r by factorial r. So it is the coefficient of t to the power r by factorial r in the expansion in the expansion of expectation of e to the power tx. So with the help of this function, we can easily calculate the rth order moment. And how can we easily calculate the rth order moment? For our convenience, let me write this whole thing again on this page, so that we don't have to go back again and again. So expectation of e to the power tx, we have got 1 plus t by factorial 1 mu 1 dash plus t square by factorial 2 mu 2 dash, and what was the rth order moment? That was t to the power r by factorial r mu r dash. So ladies and gentlemen, if I have to calculate mu 1 dash, did you notice what we can do? We can differentiate. We can differentiate what? We can differentiate expectation of e to the power tx with respect to t, and in that I can put t is equal to 0. I will get mu 1 dash. Did you realize this? If you differentiate it one time with respect to t, what will you get? Just to explain to you, you will get this term will become 0, right? Listen it very carefully. This term will become 0 and this term will become 1. Derivative of t will become 1, and you will get mu 1 dash. And if you differentiate this, you will get 2t term, right? If you differentiate the next term, you will get t square term, because the next term will be t cube. Means if you differentiate it once with respect to t, let me write, otherwise you will get confused. Suppose I write d by dt of expectation of e to the power tx. So what I will get? I will get 0 plus mu 1 dash plus 1 by factorial 2 and 2t into mu 2 dash, and so on. This is the general term. So I will get what? I will get here r t to the power r minus 1 by factorial r and mu r dash, and so on. So if I put at t is equal to 0, what I will get? At t is equal to 0, this term has a t, the next term will also have t, because if you have t square here, the next term will be t cube here. So every term will have a t, and if you put t is equal to 0, all the terms will become 0. So what you will get? You will get d by dt of expectation of e to the power tx at t is equal to 0 will give you nothing but mu1 dash. And similarly, if you think it carefully, I am writing it, but I would like you to think about this, that if I have to calculate mu r dash, what I will do? I will differentiate what? Differentiate this moment generating function with respect to t r times. So I will take rth order derivative of expectation of e to the power tx, and in that I will put t is equal to 0. I will get mu r dash. This is important to remember. This is a star result. So because expectation of e to the power tx is helping us to calculate the rth order moment, that is why it is known as moment generating function. So to summarize the things, I am repeating what is moment generating function of the random variable x. It is the expectation of e to the power tx. And how do we get the moment, rth order moment, which I am representing by mu r dash, and which is nothing but expectation of x to the power r. Yes or no? So don't get confused that what is mu r dash. It is nothing but expectation of x to the power r. And how do I get? We first write a moment generating function of e to the power tx, and then we differentiate it r times with respect to the parameter t, and then we put t is equal to 0. What we get is nothing but mu r dash. Okay. I talked about moment generating function of a random variable x about origin. Now I can also talk about moment generating function of random variable x about any point, that is x is equal to a. So when I was talking about moment generating function about origin, I was calculating the expectation of e to the power t into x, but here I will calculate the expectation of e to the power t times x minus a. So just the way we have done it earlier, if I write the expansion of it, it will look like 1 plus t times x minus a by factorial 1 plus t square by factorial 2 x minus a square, and so on. The general term will be t to the power r by factorial r, right, x minus a to the power r, and so on. So if I again use the property of expectation, it will be 1 plus t by factorial 1 and expectation. So I am writing mu1 dash expectation of x minus a. The expectation of x minus a here about the point a is I am representing by mu1 dash, then t square by factorial 2, and this will be mu2 dash, and so on, t to the power r by factorial r, and this will be mu r dash, and so on. Where what is mu r dash? Here mu r dash I am defining as expectation of what? X minus a to the power r, right? That is the rth order moment, that is rth order moment about x is equal to a. This is just for the sake of completeness. I will be focused on moment generating function about origin. Okay. So there are two properties which I have highlighted here. Sometimes they ask this in MCQ question, that mcx of moment generating function of the random variable cx is equal to mx ct, where c is being a constant, and similarly moment generating function m x1 x plus x2 plus xn t can be also written as m of x1 t into m of x2 t up to m of xn t, right? So just in case if you are interested, a student, and you want to do the proof, you should certainly do the proof. Okay. But after giving you the basic idea, what I am going to discuss next is important, and I am going to talk about the moment generating function of binomial distribution. If you have watched the video till here, please continue till the very end, because here you will get the understanding that what I was discussing earlier, because earlier thing was slightly more theoretical. Now it will give you certain practical context about this. Okay. So let us talk about the moment generating function of the binomial distribution. I hope you remember the probability distribution for binomial distribution, that is probability of x number of success is equal to ncx p to the power x q to the power n minus x, where this x can take value from 0 to n, right? I hope you remember this. Now what is the moment generating function? That is m of xt, right? The random variable here is x, so it is expectation of e to the power tx, right? What is, and this is a discrete probability distribution, so I have to take the summation. X varies from where to where? X varies from 0 to n. E to the power ts x, and then the probability. So what is probability here? Probability here is ncx p to the power x q to the power n minus x. I hope this is what we have written here. You just see the previous thing, that moment generating function. So summation e to the power tx f of x, and I am doing the same thing here, that I am taking the summation of e to the power tx into its probability distribution, and in case of binomial the summation runs from 0 to n. Okay, so let us move forward and simplify this thing. Now I am starting from here. So we have summation x varying from 0 to n, and we have the term ncx, right? So I am writing here ncx first, and we have e to the power tx and p to the power x. So if you look at this, it can also be written as p into e to the power t and whole to the power x. I hope you remember this, that x to the power x into y to the power m can be written as x to the power m into y to the power m. So I have just combined this term and this term. I am slow because you should understand it carefully, and this may be asked in the exam also. So p e to the power tx and q n minus x. Now if you write its expansion, what is the first term? If I take x is equal to 0, I will get nc0 p e to the power t to the power 0 and q to the power n. If I take x is equal to 1, I will write nc1 p into e to the power t to the power 1 and q to the power n minus 1, and so on. If I write the last term, x is equal to n, so this will become ncn p into e to the power t to the power n and q to the power n minus n, so it will become 0. I hope all of you remember the binomial expansion. How many of you remember the binomial expansion? If you don't, I am writing it for your convenience here, a plus b to the power n, and this is why the videos become longer, because I want everyone to understand it, so I am explaining in the detail. So a plus b to the power n is nc0 a to the power n b to the power 0 plus nc1 a to the power n minus 1 b to the power 1, and so on. If you write the last term, it is ncn a to the power n a to the power 0 and b to the power n. So you can see the power of a decreases, n minus 1, n minus 2, and so on, and the power of b increases. So here did you notice that it is nc0, you can see, compare b to the power a to the power n, so here we have q to the power n. So the powers of q are decreasing, q to the power n, q to the power n minus 1, and in the last we have q to the power 0, and here the powers of p into e to the power 0 is increasing, 0, 1, and the last n. So basically this is nothing but q plus p e to the power t to the power n. So the first question that they may ask you, that which of the following is the moment generating function for the binomial distribution? The first answer is that the moment generating function for the binomial distribution is given by q plus p into e to the power t whole to the power n, right? Where you understand that p is the probability of success, q is the probability of failure. So this is the first thing I have got. Now I got the moment generating function. Now I want to get the mean and variance. So what is the mean? mean of a distribution is nothing but expectation of x. And what we are calling expectation of x? We are calling it mu1 dash. And how do you define the variance? Variance of x is expectation of x square minus expectation of x whole square. So that is nothing but what is expectation of x square? That is mu2 dash and minus mu1 dash whole square. So this mu2 dash is the second order moment and mu1 dash is the first order moment. So how do you calculate this? So to calculate this, I am rewriting the moment generating function, that is q plus p e to the power p into e to the power t whole to the power n. This is my moment generating function. And suppose I want to calculate mu1 dash. So what I told you, that if you want to calculate the rth order moment, you have to differentiate the moment generating function r times, and then you have to put t is equal to 0. So if you want to calculate the first order moment, means mu1 dash, you first differentiate the moment generating function one time. So if I differentiate it one times, I will get what? D by dt of q plus p e to the power t whole to the power n. So that is equal to, let me write it over here, n q plus p e to the power t whole to the power n minus 1. And then using chain rule, q is a constant and I have to differentiate this again with respect to t. So it will give me 0, and p into e to the power t will give me p into e to the power t, right? So what is mu1 dash? Mu1 dash is d by dt, the first derivative of the moment generating function at t is equal to 0. So here I have to put t is equal to 0. So if I put t is equal to 0, n q plus p e to the power 0 to the power n minus 1 into p e to the power 0. So what did I get? E to the power 0 is equal to 1, right? E to the power 0 is equal to 1. So I get n and q plus p to the power n minus 1 into p. And we know for a binomial distribution, we know that sum of probability of success plus failure is equal to 1. So this is q plus p is basically 1. So 1 to the power n minus 1 is 1. So what we get is n into p. So what we have got? We have got mu1 dash is equal to np. And if you remember, when I talked about the binomial distribution, I told you that mean of the distribution, that is expectation of x, which we are calling as mu1 dash, is equal to n into p. So this is the second part. But we also want to calculate the variance. So to calculate the variance, we have to find mu2 dash, because the formula of variance is mu2 dash minus mu1 dash square. So first let us find mu2 dash. How to find mu2 dash? For that we have to differentiate the moment generating function. How many times? 2 times, because we want the second order moment. So d2 by dt square of mxt. And means we already have differentiated it once and we have got, so I'm going to use the earlier result. So I'm writing d by dt of, and here n and p, I can write n into p. I'm just collecting the constant term, e to the power t into q plus p e to the power t whole to the power n minus 1. So I'm continuing here. np is a constant, write it outside. And take the product rule. So this is your first function and this is your second function. So first function, derivative of second function, so it will give me n minus 1 into q plus p e to the power t whole to the power n minus 2. And you have to differentiate this again with respect to t, so that will give you p e to the power t. So that is the derivative, plus second function q plus p e to the power t whole to the power n minus 1, and derivative of e to the power t is e to the power t. So this is mu2. Sorry, I made a mistake here, because this is the second order derivative. To calculate mu2 dash, I have to take the value at t is equal to 0. So don't write it mu2 dash. To write mu2 dash, I am writing it here now. So let me change the color. So what is mu2 dash? Mu2 dash means I have to put in this expression t is equal to 0. So at t is equal to 0, should I write directly? So np is already written, right? And if I write t is equal to 0, e to the power 0, e to the power 0 n minus 1, q plus p e to the power 0 to the power n minus 2, p e to the power 0 plus q plus p e to the power 0 whole to the power n minus 1 into e to the power 0. I will be moving to the next page, but before that let us be clear. So this becomes 1, this will be n minus 1, and this will be q plus p. E to the power 0 is how much? 1. So q plus p to the power n minus 2. So this thing will become 1 because q plus p is 1. So from here I will get n minus 1 into p, and from here I will get 1, right? So should I move to the next page to write this? So what is mu2 dash? Let me write again. So you see I am writing np is there, so I am writing np, right? And in the bracket we have this term 1, so n minus 1, this term is also 1, so we have n minus 1 into p. You can do it yourself also. So n minus 1 into p, and from the second term what we get, you see this term becomes 1, this term also becomes 1, so I will just get 1. So I got 1. So I got how much? I got np into n minus 1 p plus 1. I hope everything is clear up to this. So mu2 dash can also be written as n into n minus 1 if I multiply this, and then this becomes p square, n into n minus 1 p square plus np. So what is the variance? What is the formula of variance? The formula of variance is mu2 dash minus mu1 dash whole square. And if you find it difficult to remember, you can also remember expectation of x square, that is mu2 dash, minus expectation of x, that is mu1 dash whole square. So I have got mu2 dash, that is n into n minus 1 p square plus np. And what is expectation of x? So expectation of x, the mean I have got np, so I write here n square p square. So if you simplify this variance of x, so what will you will get? N into n minus 1. So this term will be giving you n square p square, and minus np square plus np, and minus n square p square. So you can see this term and this term is cancelled. So what we are getting? N minus np square plus np. So np can be taken common. I will get 1 minus p, and that is equal to np into q, because we know that p plus q is equal to 1. So the mean, what is the mean? The mean is np, and what is the variance? The variance is equal to npq. So you can clearly see that mean is np, and in variance we are getting np into q, and q is a value which is less than 1, greater than 0. So np cube will be certainly less than np. So in this case mean will be greater than variance. I hope you understood this. Np is a, suppose np is a quantity, and in that quantity you are multiplying by q. Q is a quantity less than 1, so that quantity will become less than the original quantity. So that is why the mean is greater than variance, and this is an important result which they ask sometime in multiple choice question. So I hope by now you are clear about the moment generating function of binomial distribution and how to calculate its mean and variance. So let's move to the Poisson distribution case now, and Poisson distribution case is even easier to calculate. So let us do it quickly, and I think we already have got some context, so we will be able to do it quickly now. But before I write it, I hope you remember that probability of x is equal to x number of success is, in case of Poisson distribution, is e to the power minus lambda by lambda to the power x by factorial x. And here in case of Poisson distribution, that x can take value 0, 1, 2 up to infinity, right? I have told you in the previous video that x can take indefinitely large number of value. So how do you calculate the moment generating function? To calculate the moment generating function, you take expectation of e to the power tx, right, which is nothing but How do you calculate expectation? This is a discrete probability distribution, so summation varies from x is equal to 0 to infinity, and e to the power tx into the probability, that is e to the power minus lambda, lambda to the power x by factorial x. This is how you calculate the expectation, that the function of x, which is e to the power tx now, into its probability. Now I have to simplify this. So how to simplify? Let me change the color and be very careful, because they may ask you this question. So x is equal to 0 to infinity, right? Now ladies and gentlemen, you look at this term e to the power minus lambda, which is constant, not depending on x. And if you look at this term here and this term here, both of this term can be written as lambda into e to the power t whole to the power x. I combined these two terms and then I wrote it factorial x. Now just to save space, I am continuing this side. E to the power minus lambda is a constant, so it can be taken out of summation. And here we have the summation x varies from 0 to infinity, lambda into e to the power t whole to the power x by factorial x. Using the summation, if I write this expansion, I will get what? E to the power minus lambda. If I take x is equal to 0, the whole thing, this to the power 0 by factorial 0, so it will become 1. If I take 1, I will get lambda e to the power t by factorial 1. If I take 2, I will get lambda e to the power t whole square by factorial 2. If I take 3, I will get lambda e to the power t to the power 3 by factorial 3. And I hope now you are smart enough to understand that this is nothing but the expansion of e to the power lambda e to the power t. Okay, so if I just combine these two terms, e to the power minus lambda and this, what I will get? E to the power lambda e to the power t minus lambda, which is nothing but e to the power lambda common e to the power t minus 1. So this is the first result I have got, that what is the moment generating function of a Poisson distribution. So this is equal to e to the power lambda into e to the power t minus 1. You need to remember this because that may be asked as a MCQ question. What was the moment generating function for Poisson distribution? Do you remember? It is q plus p e to the power t whole to the power n. For Poisson, this is this. Now once we have got the moment generating function, next we have to find the moments. So the first moment is mu1 dash. So to find the mu1 dash, we are going to differentiate the moment generating function one time with respect to t. So d by dt, and what I have got? I have got e to the power lambda into e to the power t minus 1. So if I do this in a differentiation, first using the chain rule, I will write e to the power lambda e to the power t minus 1, and then I have to differentiate this again with respect to t. So lambda is a constant and derivative of e to the power t minus 1 will be e to the power t, right? Now how do you get the mu1 dash? You get mu1 dash by putting in d by dt of mxt, you put t is equal to 0. So if you put t is equal to 0 here, what you will get? You will get e to the power lambda and e to the power 0. Should I write it? Or okay, let me write e to the power 0 minus 1 into lambda e to the power 0. So e to the power 0 is 1, so 1 minus 1 is 0, and e to the power lambda into 0 is e to the power 0, and here we get lambda into e to the power 0. So these two terms are 1, so what we get is lambda. So mu1 dash, which is nothing but expectation of x, which is nothing but the mean of the Poisson distribution, mean, and that is equal to lambda. So this is the important result we have obtained. Now I want to find the variance. So to find the variance, first of all we have to find mu2 dash, and to find mu2 dash we have to differentiate the moment generating function mxt with respect to t 2 times. So we already have differentiated the moment generating function 1 times, and what we have got, you can see this result, we have got lambda into e to the power t into e to the power lambda e to the power t minus 1, right? Now lambda is a constant, so I take it outside, and we have two functions. One function is this and another function is this. So we are going to use the product rule. So first function e to the power t. We have to differentiate this again with respect to t. So e to the power lambda into e to the power t minus 1, and into, if I use the chain rule, I will get lambda e to the power t. Now the second function e to the power lambda e to the power t minus 1, and derivative of e to the power t is e to the power t. I would suggest you that you do all this calculation yourself so that you don't get confused. And in case if you find it difficult, then you can check. So mu2 dash will be what? Mu2 dash will be d2 by dt square of mxt at what point? At t is equal to 0. I am going to do this calculation directly. I am not going to write all the details. So lambda here, right? E to the power 0 will become 1, and this term e to the power 0 will become 1 minus 1 0, so it will become e to the power 0. So this will also become 1, and this will also e to the power 0 will become 1. So I will get just lambda plus, here if you look at this term, e to the power 0 1, so 1 minus 1 is 0, lambda into 0 is 0, so it will become e to the power 0, so 1, and e to the power 0 is again 1, so it will be 1. So what we got? We got lambda square plus lambda. So that is mu2 dash. So what is the variance of x? Variance of x is expectation of x square minus expectation of x whole square. So that is mu2 dash minus mu1 dash whole square, and mu2 dash I have got lambda square plus lambda, mu1 dash I got lambda, so its square will be lambda square, so I cancelled it. So what is the variance? So variance of x is also lambda. So for Poisson distribution, we noted that mean and variance both are same, and that is equal to lambda. For binomial, the mean was greater than the variance. These are MCQ question that may be asked. Okay. So by now we have calculated the mean and variance of two spatial distribution. The next we are going to talk about mean and variance of negative binomial distribution, and here a lot of computation will be involved, so have patience and listen it very carefully, and I hope you are also using a pen and paper and doing it together with me. So let's start. So before I write the moment generating function, I hope you remember what is the probability distribution in case of negative binomial distribution, and this is also a discrete probability distribution. I hope you remember that. So that is given by B star. We have used this notation, B star x k p. So where p is the probability of success, k is the number of success in x number of trials, right? In case if you have doubt, please watch the negative binomial distribution video, and it was x minus 1 c k minus 1 p to the power k q to the power x minus k. Yes or no? And the x was taking value from starting from k plus 1 k so on up to infinity, because to get k number of success you must have to perform at least k number of trials. We have discussed in detail. So let me write the moment generating function, that is mxt, and be very careful because this may be slightly more complicated than the other two. So expectation of e to the power tx, right? And expectation of e to the power tx, so here the summation will start from x is equal to k and will go up to infinity, and it is e to the power tx, and its probability, that is x minus 1 c k minus 1 p to the power k and q to the power x minus k. For our convenience, will you allow me to write this term? You can write it in the second step, but just to save a space I am writing q to the power x by q to the power k. Okay. Now continuing this, here I am writing. Now see, p to the power k and q to the power k are constant, so I take both these terms out of summation, p to the power k, q to the power k, and in the summation what we are left with? We are left with let me first write the limit xk from k to infinity, and here we have x minus 1 c k minus 1, and we have q to the power x term and we have e to the power tx term. So both of them can be combined and it can be written q e to the power t whole to the power x. Okay, and if I write its expansion, what it will be? It will be like, should I write here in the bottom? Let me write here in the bottom. So its expansion will be p to the power k q to the power k, and I have to start at x is equal to k. So this will be k minus 1 c k minus 1 and q e to the power t whole to the power k. What will be the next term? Because I am starting at k, the next term will be k plus 1. So in place of x you will put k plus 1. So k plus 1 minus 1 will become k c k minus 1 q e to the power t whole to the power k plus 1. Then if you put k plus 2, it will become k plus 2 minus 1. So that is k plus 1 c k minus 1 q e to the power t whole to the power k plus 2, and these terms will continue up to infinity. Now listen it very carefully, otherwise you will not follow. Now if I rewrite this, it will become p to the power k q to the power k, and you see in each of this q e to the power t and whole to the power k can be taken common. So I am taking q into e to the power t whole to the power k common, and k minus 1 c k minus 1, so that is equal to 1. I hope you remember this result, that ncn is equal to 1. The second term is k c k minus 1. So what is k c k minus 1? If you expand it, it will be factorial k, or it can also be seen as simply kc1. I hope you remember that there is a result that ncr is ncn minus r, but anyway I am explaining it. So factorial k by factorial k minus 1 into k minus 1, right? So this will become 1. Factorial 1 is 1, and k minus 1 factorial will give me k. So this term will give me k, and I already have taken q e to the power t to the power k common, so I will be left with q e to the power t term only. Similarly, if you evaluate this term, you will get how much? You will get, let me just do the evaluation. So k plus 1 factorial divided by k minus 1 factorial and into k plus 1 minus k minus 1. So this will be basically 2. K cancel, it will be factorial 2, and there you will have k plus 1 into k. So I will be getting how much? I will be getting k plus 1 into k by 2 and q e to the power t whole square, and so on. Now if you look at this expansion, see there are many things in maths that you need to remember. We have studied one such result in our previous classes, and that result is that what is the expansion? If I write it 1 minus x to the power minus n, this expansion is 1 plus n into x plus n into n plus 1 by factorial 2 into x square, and so on. So if you look at this expansion and this expansion, I hope you can see here in place of n we have k, and in place of x we have k square. So if I can move to the next page, this will look like what? This will look like the first term here is p to the power k by q to the power k. So I write p to the power k by q to the power k. Second term is q e to the power t whole to the power k, and this expansion can be seen as 1. So if I just for your convenience write it, this can be seen as what? This can be seen as 1 minus q e to the power t whole to the power minus k. So I'm just going to write that in the next page. So this will be 1 minus q e to the power t whole to the power minus k. So I'm now concluding this thing. So what is mxt I have got? So if you look at this expression, from this you are getting q to the power k, and if you look at this power, you have q to the power k, so that will be cancelled. And let me write it. So it will be like p to the power k, q to the power k into q to the power k e to the power tk, and this can be written as 1 by 1 minus q e to the power t to the power k. I am doing all this for your better understanding. So mxt is equal to this q to the power k, q to the power k cancel, and these two terms can be combined. So it can be written as p into e to the power t whole to the power k divided by 1 minus q e to the power t to the power k. So this is the moment generating function of a negative binomial distribution. I hope up to this there is no doubt. Now what is the next thing? The next thing is to calculate the mean and variance, right? So how do you calculate the mean and variance? So the first thing is that we have to differentiate to calculate mu1 dash, sorry, we have to differentiate the moment generating function with respect to t. So to differentiate it, I am writing d by dt and p e to the power t to the power k, okay. And for using the product rule, using the product rule will be easier. We can also use u by v, but I am using the product rule. So for our convenience, I am writing it minus k, right? So just what is the first term? First term is p e to the power t whole to the power k. I have to differentiate this second term, so it will give me minus k 1 minus q e to the power t to the power minus k minus 1, and then again I have to differentiate it, so it will give me minus q e to the power t, okay. And then the second term, so 1 minus q e to the power t to the power minus k, and derivative of this, so k into p e to the power t, let me write here in the bottom, otherwise it will look complicated. Let me write this term here in the bottom. So plus the second term, that is 1 minus q e to the power t to the power minus k, right? And then the derivative of this, so k p e to the power t k minus 1, and then again we have to differentiate it, so I will get p e to the power t, okay. So you just collect the terms now. I am using a different thing so that it does not look complicated. So you see here you have minus k and you have minus q, so minus and minus will become plus, so it can be written as kq, and you have e to the power t and p e to the power t to the power k, so I write e to the power t, and the second term, that is p e to the power t whole to the power k divided by, and this is 1 minus q e to the power 2 to the power k minus 1, so I write it 1 minus q e to the power t, and in the denominator it will become plus 1. What is the second term? Second term is k, so I write k here, and then we have p, so I write p here e to the power t, and one more thing I can do. So you have p e to the power t, k to the power k minus 1, and p e to the power t. So if I combine it, it will become whole to the power k, right? And divided by 1 minus q e to the power t to the power k. So now see, there are certain things that we can take common. We can take k common and this whole thing common. So k common, and here we can take p e to the power t to the power k common divided by 1 minus q e to the power t to the power k common. So in the bracket, from this I already have taken everything common, so I will get 1 plus, and what extra terms we are left with here? We are left with here q e to the power t, so I am getting q e to the power t by 1 minus, and here it is power k plus 1, so 1 minus q e to the power t, right? Now I am going to move to the next page. Now if you add this, you see it will go into the denominator, so 1 minus q e to the power t and plus q e to the power t, so it will cancel, so I will get 1 by 1 minus q e to the power t. So what can be written as? So I can write it that this is equal to, in the numerator I am getting k into this p e to the power t whole to the power k. I hope it is power. So k into p e to the power t and whole to the power k, and in the denominator what I will get, 1 minus this thing to the power k, and from this I will get 1 by 1 minus q e to the power t, so the power will be added, so I will get 1 minus q e to the power t whole to the power k plus 1. So this is our the first order derivative d by dt of mxt. Yes or no? It looks bad. Let me rewrite it. So this is mxt. Yeah, complicated our calculation, but anyway we are managing it. So moving ahead, what we have to do next, we have to at t is equal to 0. I am writing just to save a space. At t is equal to 0, if I calculate d by dt of mxt, what I will get, and that is equal to mu1 dash. So look at this, e to the power 0 will become 1, it will become k into p to the power k divided by, here e to the power 0 will become 1, so it will become 1 minus q, and 1 minus q to the power k plus 1. So what you get mu1 dash is equal to k into p to the power k divided by p to the power k plus 1. So I get what? I get this is equal to k by p. So I have got the first result, that is mean is equal to k by p, right? This is the first result. I hope up to this there is no doubt. We already have like completed more than 50 minutes, but anyway it will be a longer video, I told you in the beginning itself. Now the next thing that we have to do is that we have to calculate the second order derivative of this to calculate the variance. So we have to calculate d2 by dt square of mxt. So this is the first order derivative I already have calculated. So basically I have to calculate d by dt of k into p e to the power t to the power k, and again for our convenience I can write it 1 minus q e to the power t whole to the power minus k minus 1, so that we can apply the product rule easily. Now k is a constant, so I write it outside. There are two functions, this is the first function, this is the second function. So I write the first function p e to the power t whole to the power k, and derivative of second function, so minus k minus 1, 1 minus q e to the power t minus k minus 1, so minus k minus 2. Okay, and then I have to differentiate this again, so minus q e to the power t. So this is the first term. Now what is the second term? So plus second function 1 minus q e to the power t to the power minus k minus 1, and derivative of this, so k into p e to the power t to the power k minus 1, and derivative of this will again give me p e to the power t. Long calculation, but I hope we are getting it. Now let me change the color so that there is no confusion. So k is a constant, right? And if I look at the first term here, we have a minus q term and we have a minus k plus 1 term, so that will become plus minus minus plus. So I will get k plus 1 into q, and we have p into e to the power t whole to the power k, right? And q e to the power t, so I write q e to the power t and then p e to the power t whole to the power k. I hope I have collected all the terms, k plus 1 this term and q here, so both no, there was no need to write this q because I already have written q e to the power t. So let me remove this q, right? So minus minus plus, k plus 1 and q e to the power t and p e to the power t to the power k divided by, if I take it in the denominator I will get 1 minus q e to the power t whole to the power k plus 2. And what will be the second term? So second term will be this k here right? So I write k, and then you have p e to the power t to the power k minus 1 and p to the power t. So it will be p e to the power t whole to the power k, and this is divided by 1 minus q e to the power t whole to the power k plus 1. I hope up to this there is no doubt. Yes or no? Now I have to move to the next page, but before I move to the next page, I just want to see that there are certain things that can be taken common. So what we can take common, I can take p into e to the power this term common, and here we have power k plus 2 and power k plus 1. So power k plus 1 can be taken common. So this term will give me k in the bracket, and this term will give me q into e to the power t into k plus 1 by this. So let me write it. If I continue, I hope you are doing it together. So k is already outside, and then we are taking p into e to the power t common. So I will get p into e to the power t to the power k common divided by 1 minus q into e to the power t whole to the power k plus 1. So 1 minus q into e to the power t whole to the power k plus 1. So this is common, and what we are getting in the bracket, just let me see. So this thing I am getting k from the second term, so I am writing the second term first, and what I am getting from here, I am getting k plus 1 into q e to the power t. So I am writing k plus 1 into q e to the power t divided by 1 minus q e to the power t. You just do your own calculation. Don't be dependent on this, so that it will be easier for you to follow. So k into p e to the power t whole to the power k divided by 1 minus q e to the power t to the power k plus 1, and if you simplify this thing, you will get k minus kq e to the power t, and in the numerator kq e to the power t plus q e to the power t, and the whole thing can be divided by 1 minus q e to the power t. Now we are at the final step. So this term and this term cancel. This is the same term as like this. So from this I am getting k and into p e to the power t whole to the power k, and from this I am getting k plus q into e to the power t, right, and divided by 1 minus q e to the power t whole to the power k plus 2. Okay, so what is mu2 dash? Mu2 dash means we have to put t is equal to 0 in this. So just to save space, I am writing here. So if I put t is equal to 0, what I will get? K. E to the power 0 is 1. So I will get k into p to the power k. And if I put e to the power 0 here, I will get how much? I will get k plus q, right, because e to the power 0 will become 1 divided by 1 minus q, because e to the power 0 is 1 minus q to the power k plus 2. So what is the mu2 dash we are getting? Mu2 dash we are getting k into p to the power k into k plus q, and 1 minus q is basically p, so that will give me p to the power k plus 2, right? Now p to the power k plus 2, so this will cancel. So in the numerator, k into k plus q divided by p square. So what we got? We got k square by p square and plus k into q by p square. After a long and very difficult computation, we have arrived here. So now let me calculate the variance of x, that is mu2 dash minus mu1 dash whole square. So mu2 dash we have got k square by p square plus k into q by p square, and what was the mu1 dash we got? Mu1 dash we got k by p, so its square will be minus k square p square. So we cancel this term and this term, So we got k into q by p square. So finally we have got everything. The mean was k by p, and what is the variance? The variance is kq by p square. So for negative binomial distribution, the computation was slightly more complicated and it has taken me 1 hour. But anyway, before I end, let me also talk about moment generating function of geometric distribution. Okay, so first of all, what is the probability distribution in case of geometric distribution? So it is given by gxp is equal to p into q to the power x minus 1, and x can take its value from 1 to up to infinity. For detail, watch the other video which I already have uploaded. So what is the moment generating function? We are using the same concept, m of xt. So it is expectation of e to the power tx, which is equal to, in this case also it is a discrete probability distribution, so e to the power tx into p q to the power x minus 1, and here x varies from 1 to infinity. So you can clearly see that here it is. Let me write it otherwise. So I write it x is equal to 1 to infinity e to the power tx into p into q to the power x by q. Q to the power x minus 1 can be written like this. Now there are two constant terms like p and q, which is independent of x. So I write p by q common out of summation, and here in the summation we have x varying from 1 to infinity, and we have e to the power tx term and q to the power x term. So that can be written as q e to the power t whole to the power x. So now if you write the expansion p by cube, it is q into e to the power t, if I take x is equal to 1, plus q into e to the power t square plus q into e to the power t cube, and so on. Now this is equal to what? This is p by q, and I hope you know the GP progression, geometric progression. So if you look at this as the first term and this as the common ratio, and this is an infinite series, so it can be written as q e to the power t by 1 minus q e to the power t, where we assume, because we want their convergence, we have used a term absolutely convergent, if you remember when I was discussing in the beginning. So for that, this mod value of q e to the power t should be less than 1. Just to give you the context, I hope you remember that we have studied in our previous classes that if the infinite series is a plus ar, not ar square, a plus ar and plus ar square and so on up to infinity, then its sum is a by 1 minus r, where we assume that mod of r is less than 1. So this is what we are writing here. So we have got the mxt, right? We have got the mxt, and what is mxt? So if you see, this q term and this q term is cancelled, so we are getting p into e to the power t divided by 1 minus q e to the power t. So this is the first thing, right? The moment generating function. For the fourth distribution we have got it. Now the next thing, we have to find the mean and variance. So to find the mean or variance, first of all we differentiate the moment generating function with respect to t. So d by dt of what is the moment generating function? P into e to the power t divided by 1 minus q into e to the power t, 1 minus q into e to the power t. So how do you differentiate it? Using u by v formula. So denominator 1 minus q e to the power t, derivative of this, so p e to the power t minus p e to the power t, and derivative of this will give me minus q e to the power t. The whole thing is divided by 1 minus q e to the power t whole square, right? So if you simplify it, what will you get? Can I write it directly? You have minus and you have here p, so pq e to the power t into e to the power t, and if you look at this minus and this minus, it will become plus. So pq e to the power t so these two terms will cancel, plus and minus term will cancel. So in the numerator you will get p e to the power t divided by 1 minus q e to the power t whole square. So this is your d by dt. Now to calculate the mu1 dash, we have to take d by dt of mxt at t is equal to 0. So if I put t is equal to 0 here, I will get p e to the power 0 is 1 and 1 minus q e to the power 0 is 1, so a square. So I get p by 1 minus q square, so that is p by p square, so that is equal to 1 by p. So mean is equal to expectation of x, which is represented by mu1 dash is 1 by p. Point number 2. Point number 3 now. So we have to find second order derivative d2 by dt square of mxt, and this, for our convenience, we already have got the first order derivative. So d by dt of p into e to the power t by 1 minus q e to the power t whole square. So this is equal to, let me change the color. So denominator 1 minus q e to the power t whole square, derivative of this, that is p e to the power t minus p e to the power t. If I differentiate this, I will get 2 into 1 minus q e to the power t, and into again minus q e to the power t. I hope you are aware about the chain rule, and divided by here, if I do the square, 1 minus q e to the power t to the power 4. So if you do the simplification, what will you get? So before I do the simplification, what I am going to do for our to making the computation easier, we can put t is equal to 0 at this place itself. So if I ask you what is mu2 dash, I put t is equal to 0 in this expression itself, so that it becomes easier. So I get 1 minus e to the power 0 will become what? E to the power 0 will become 1, so it will become 1 minus q square, and p, so I get p here. E to the power 0 will become 1, and here p is there. E to the power 0 will become 1, so p into 2 into 1 minus q e to the power 0, so it will become 1 minus q, and here we have minus, right? So I write in bracket minus q, e to the power 0 will become 1, and the whole thing is divided by 1 minus q to the power 4. Now I can write one final step here. So what I'm getting 1 minus q square. So let me change the color to avoid any confusion. We will be getting 1 minus q is p square and into p, and this minus and this minus will make it plus. Here we are getting 2 and q into p, so 2p cube, and 1 minus q is also p, so 2pp means 2p square q divided by 1 minus q to the power 4, so that is p to the power 4. Okay, now there is no space, I have to move forward, so let me write it. So what we have got mu2 dash is equal to in the numerator p into p square plus 2p square cube. So in the numerator we have got p into p square plus 2p square cube, and in the denominator we have got p to the power 4. So you can simplify it. If you separate it, you will get 1 by p term, p cube by p to the power 4, that is 1 by p, and plus you will get 2 cube by p square, right? Now this is mu2 dash. What is the variance? The variance is mu2 dash minus mu1 dash whole square. So that is equal to 1 by p plus 2 cube by p square. And what was mu1 dash? Mu1 dash was also 1 by p. So it will be minus 1 by p square. Okay. So if you simplify, you will get what? LCM will be p square. And you will get here p plus 2 cube minus 1. So this can be written as what? This can be written as p plus cube. P plus 2 cube can be written as p plus q minus 1 divided by p square. And what is p plus q? P plus q is 1, so 1 plus q minus 1 by p square. So what we get? We get this is equal to q by p square. Okay, so we have got every detail here. The mean is equal to 1 by p, and the variance is equal to q by p square. So this was a long video, almost 70 minutes, but I have covered everything and it has taken me a lot of effort. But anyway, this is what I can do for the student. But what you can do to just appreciate it, you share it with everyone, ask others to join the channel and like the video. Thanks for watching this long video. Have a very great day.